Back in my day, it was 1908, and we still didn't know the charge of an electron. J. Thomson discovered it more than a decade ago, and scientists were arguing about whether it was a fixed or a variable value. I was 40 then, and I had achieved a doctorate and PhD in physics at the University of Columbia. Physics was just so fascinating to me, but there was one thing that remained a mystery to me, and that was the charge of an electron. So, between 1909 and 1913, I built and used this magnificent apparatus to conduct the experiment over a number of years, to finally quantize the charge of an electron. Let me show you how.
I'll show you how the experiment worked. The oil drop experiment consisted of an apparatus that included a closed chamber separated into an upper and lower compartment, an atomizer, a light source, an X-ray, a microscope to observe, electrically charged plates, and a variable power supply. Before Milikan could determine the charge of an electron, he had to turn the oil into a fine mist to ensure that the droplets would remain whole during its suspension in air. This was achieved through the use of an atomizer, which uses Bernoulli's principle to move and disperse a bulk liquid into finer droplets. As air passes through the horizontal tube, the oil ascends up into the tube and follows the stream of fast-moving air. As the air leaves the nozzle, it expands as it tries to fill the greater volume of the upper chamber, which in turn splits the oil that it is carrying into fine droplets. As the droplets fall into the lower chamber, they may carry either a positive or negative charge due to friction. Hence, Milikan used an X-ray source to ionize the air and ensure the oil droplets had a negative charge.
As the now ionized oil droplets continue to fall into the second chamber, there are two main forces acting on the droplet: gravity and air resistance. Millikan recognized that the mass of the droplets were not uniform throughout. Thus, he observed the droplets fall at different rates due to the gravitational and frictional forces acting at different magnitudes. Opposing the force of gravity is the frictional force of air, acting in an upward direction. The magnitude of air resistance is dependent on various factors, such as size, shape, and viscosity, where the greater the viscosity, the greater the drag experienced.
After turning on the electric field, there is a clear change in the velocity of the oil droplet. The total forces acting on the oil droplet now include gravity, air resistance, and the force of the electric field. If the electric field creates a force greater in magnitude than gravity plus air resistance, then the oil droplet would ascend upwards. This is because the negative charge of the electron experiences the electric field at a greater force than gravity, hence repelling from the negative plate and becoming attracted to the positive plate.
The adjustment of the potential difference between the two plates correlates to how much the oil droplet is attracted/repelled. If the voltage is set too high, then Fe is greater than Fg, and the oil droplet would ascend upwards. If the voltage is set too low, then Fg is greater than Fe, and the oil droplet would descend. As such, the careful manipulation of the voltage allowed Millikan to suspend the droplet in air. By reaching an equilibrium state, where F net is equal to 0, Millikan equated Fg to Fe, where Mg is equal to Eq. Hence, by rearranging the equation to make Q the subject, Millikan had an equation that could solve for the charge. However, because he couldn't determine the mass of the droplet, he couldn't calculate the force of Fg. This was overcome by using a crosshair that allowed him to measure the radius of the spherical droplet. Following this, he calculated the volume of this droplet and multiplied it by the uniform density of oil to determine the mass of the droplet using the formula shown. Then, he was able to input the gravitational force and field intensity to calculate the amount of charge in the droplet observed.
However, this value indicates the amount of charge in that particular droplet, not the charge of a singular electron. As such, there could be more electrons in droplet A than droplet B. Going into the experiment, Millikan didn't know whether the value of the charge was continuous or discrete, and thus sought to distinguish a pattern through the collection of a great deal of data. This also ensured that the data accounted for the difference in the number of electrons that each droplet carried. During his analysis, Millikan determined the existence of a pattern by finding the highest common factor, where at least one of the droplets carried a singular electron. If there was no pattern found, it would mean that the charge of an electron is continuous, where there will be an infinite amount of random results. By finding the highest common factor, Millikan found a constant charge value of 1.5924 times 10 to the power of negative 19 coulombs, hence determining that the charge of an electron is discrete. However, this value was later determined to be slightly lower than the current accepted value of negative 1.602 times 10 to the power negative 19 coulombs.
Hey, it was within 1%.
Not good enough.